Algebra 2 Cram, New York State, Algebra 2 Regents, Common Core, Basics, Trigonometric Functions, Concept number 19, Sine and Cosine Trends. The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. What we're doing here is super effective. I'm coaching you to turn your wants and desires of getting an A or perfect test scores into a brand new paradigm. I want to include everyone who needs a boost in Algebra 2, and if I could stick every single math student with a syringe containing a healthy dose of eye-opening awareness of your inner mathematical genius, I probably would. So inbox me at memedicine@gmail.com to get your healthy dose of Algebra 2 by ordering the complete cram session beyond the trigonometry series. You have lots of friends, peers, classmates, and colleagues who could benefit from this cram session because they're taking Algebra 2 with you as well. So tell them to inbox me at memedicine@gmail.com so that they too can order the complete cram session, okay? And you'll be glad you spread the word because they'll make great study buddies. And last but not least, cramming often has a negative connotation, but what people are actually thinking of is hurrying, which is a result of fear and can consequently be destructive to your learning process. We're not hurrying here, we're cramming, and there's a huge difference. Hurrying is jam-packing tons and tons of unorganized information into your mental spiritual DNA over a tiny amount of elapsed time, whereas cramming is taking quantum leaps in your understanding in an organized way in what seems like an instant. Let's delve into the concept of sine and cosine trends, specifically in quadrant 1, okay? Sine and cosine trends for 30 degrees, 45 degrees, and 60 degrees. The denominator for the sine and cosine of 30 degrees, 45 degrees, and 60 degrees is the numerical value 2. What is the pattern in the numerator for the sine of theta and cosine of theta as the value of theta increases from 30 degrees to 45 degrees to 60 degrees? I'll give you a moment to think. And definitely press pause if you need to. All right, so hopefully by now you were able to press pause and arrive at an answer. And if you didn't, that's completely fine. That's why we're here to explore the concept of sine and cosine trends together, okay? But before expressing the sine and cosine for the theta values 30 degrees, 45 degrees, and 60 degrees, and just in case you're wondering, theta is a Greek letter, lowercase. I guess it's synonymous with the letter T in the English alphabet, and it's just used as a variable placeholder instead of the common variable x, because we're going to use x here to represent something else. So theta is like the second go-to variable to hold the place of an angle, okay? So in order to understand, in order to express these values and get what we're talking about, we need to first understand the concept of standard position, okay? And doing this is going to simplify finding all trigonometric values beyond the sine and cosine, okay? And because the angles 30 degrees, 45 degrees, and 60 degrees are all acute angles in standard position, which I'm going to show you in a few, all located in quadrant 1. These are all located in quadrant 1. They're going to have 7 key features, okay? First of all, I said they're acute, and that's because they're located in quadrant 1 between the quadrantal angles 0 degrees and 90 degrees, okay? So the first feature of an angle in standard position in quadrant 1 is that its vertex is located here at the origin at the location x coordinate 0, y coordinate 0, okay? And the rate on the positive x-axis, which is slightly bold, right here is called the initial side ray. The other ray terminates in quadrant 1 after the angle grows in the counterclockwise direction, and this is called the terminal side ray. But to be cute, we'll call it R for short, okay? And the fourth feature of this standard position concept is that we're gonna like play around a little bit. We're gonna cut this terminal side ray off right about here at point P, P being short for point, and it's going to have the coordinates x, y, okay, as indicated. So for our purposes, the extent of this terminal side segment, which was formerly a ray, but it's now a segment because it's bound between 2 points, the points being the origin and P, it's going to go to the extent of its x-coordinate, which we'll indicate here. So this x is synonymous with this x. They're the same things, okay? And when we resolve it into its y component, it's going to rise to the level of this y. This y is the same as this, okay? So looky, what do we have here? We have what's a right triangle. And this right triangle is the basis for finding all these trig functions, specifically in our example here, the sine and cosine functions, okay? Please hold just a second. My brother's interrupting my recording. Okay, so sorry about that. Oh, siblings, they get on my nerves. I'm sure a lot of you share the feeling with me that you wish you were an only child, because I definitely do. Anyway, okay, yeah. This right triangle is the basis, as I was previously saying, for finding all trigonometric values, okay? Alrighty then. So, yeah, we're going to continue in this train of thought. And for some trigonometric values, they'll be negative. And the negatives come from the fact that, well, the x-coordinate and the y-coordinates contribute to the fractional ratios that are going to yield our basic trig functions like sine and cosine. But because they're coordinates, they're locations on the xy Cartesian coordinate plane. Therefore, x, if located in the realm of the positive x-axis, which occurs in quadrant 1 and quadrant 4, it's going to be positive, okay? That's if the terminal side segment has an x-coordinate terminating in quadrant 1 or quadrant 4. But if the terminal side segment has an x-coordinate terminating in quadrants 2 or 3 in the realm of the negative x-axis, it's definitely going to be negative, okay? And we could say the same for y. If the resolution of the terminal side segment has a y-coordinate that terminates in quadrant 1, then it's in the realm of the positive y-axis, therefore it's going to be positive. And the same for quadrant 2. If the terminal side segment has a y-coordinate that terminates in quadrant 2, that y-coordinate is going to be positive. We can't say the same for quadrants 3 and 4 because down here we're in the realm of the negative x-axis. Therefore, if the terminal side segment were to terminate here or here, it would have a negative y-coordinate, which could make the overall trig function negative. Possibly. Sometimes this is not the case. And you'll see why in just a second, okay? So that was kind of like feature 4 and 5 along a side thrown in between there. And last but not least, the ray, the terminal side ray, or you'll notice the hypotenuse, which is opposing our 90-degree angle. It's always going to be a measurement, a segment length specifically, therefore it's never going to be negative. And I'll show you why in just a sec. Because in order to figure out the magnitude of this terminal side segment or segment length or hypotenuse, you have to use a spin on the distance formula. And because we're measuring the distance of r, or formerly the ray, now a segment, we're going to say r is equivalent to the square root of x squared, that is the x-coordinate squared, plus the y-coordinate squared, okay? And the reason why this is a variation of the distance formula is because the distance formula says the magnitude of a distance on a Cartesian coordinate plane is the square root of the final x position minus the initial x position. Well, our initial x position here is 0, so we don't have to be redundant and write in 0. Therefore, we'll leave it at the final x position of x squared plus the final x position, y position, sorry, minus the initial y position squared. Well, again, our initial y position is going to be 0. We don't have to be redundant and write that in. Therefore, we can just square the y term, okay? So we take the square root of this sum, and that's going to give us the value of our r, okay? So in short, the measurement of the segment length, or the hypotenuse, is always going to be positive. And getting back to our original question, the sine and cosine values for 30 degrees, 45 degrees, and 60 degrees depend on the fractional ratios of the x-coordinate, because the x-coordinate corresponds to the adjacent side, which is used to figure out the cosine, and the fractional ratio of the y-coordinate. The y-coordinate corresponds to the side opposite our angle theta, which is used to figure out the sine, okay? So it depends on the fractional ratios of x and y to r, how they compare to r, okay? R being our hypotenuse. And earlier, I told you that the numerical value of the denominator for all these dudes is 2. Well, that's because our hypotenuse is 2. But let me show you why. The sine of any angle theta is going to be equal to the y-coordinate, or opposing side, over the hypotenuse length, or for our purposes, y over r, the y-coordinate divided by the segment length, or the opposite side divided by the hypotenuse. And for the cosine of any angle theta, it's going to be the corresponding x-coordinate divided by the hypotenuse. But for our purposes, the x-coordinate corresponds to the adjacent side with respect to the angle theta, so that's what goes in our numerator, and r, or our segment length or hypotenuse, goes in the denominator. So obviously, if all these dudes are true, that means that r has a length of 2 in the case where the angle theta is going to be 30 degrees, 45 degrees, and 60 degrees, okay? All right, but let's continue. And so in quadrant 1, you're going to notice that the sine basically increases. It gets larger, okay? So for 30 degrees, we have 1 over 2. That means that if this angle were theta, this side would have a y-coordinate of 1, or not even necessarily. It's just that when you simplify the fractional ratios, it's 1 over 2. And then the same if this theta were 45 degrees, the fractional ratio would simplify to radical 2 over 2. And if this angle theta were 60 degrees, the fractional ratio would simplify to radical 3 over 2. So as theta basically increases or grows in the counterclockwise direction, the sine basically increases, okay, in quadrant 1. And now the opposite is true for cosine. So this is really cool. Things grow in the, well, technically you can do the square root of 1. So things grow in the consecutive square root. Okay, so square root of 1, square root of 2, square root of 3. And for the cosine of theta, with respect to 30 degrees, 45 degrees, and 60 degrees, the trend is that the numerator value decreases in consecutive square roots, starting with 3, 2, And it's understood 1 could always be represented as the square root of 1 because the square root of 1 is itself. So yeah, it's kind of neat, this trend. That's why I wanted to make this session, because I thought this was really, really cool. Okay. And again, so for theta equals 30 degrees, the fractional ratio for the cosine of theta is going to be a radical 3 over 2. When theta is 45 degrees, the fractional ratio simplifies to the square root of 2 over 2. And when theta is 60 degrees, the fractional ratio of the cosine of theta simplifies to 1 over 2. Okay? All right, so that's that. Thanks for tuning in. And as you can see, intellectual comprehension of this material was not that difficult. And after this short amount of time you take to complete this entire Algebra 2 Cram series, you'll be able to answer all the Algebra 2 concepts there are, okay? So good luck studying, and thanks for tuning in.